I bet when you code, you also have problems with legacy code. If you want to know how you can deal with that, especially in the context of medical software, stay with me. I have something to tell you. Hello and welcome. My name is Andreas Horn. I'm Senior Manager for Code Testing at Vector. And today I want to share with you a presentation that I have delivered on our Medical Engineering Day. But I think it is a topic that could be also interesting for you. So please enjoy this talk, and if you have questions, reach out to us. Then let's get started. The title of the presentation is Make, Do and Mend, IEC 62304 and Legacy Code. But before we go into the topic, I just want to shortly warn you, because I will be using throughout this presentation AI-generated content. It has been created using Microsoft Bing Image Creator, and it is purely for explanatory purposes. And any correspondence with actual places or persons is purely coincidental and not intended. So whenever you see this small AI icon on that page, it is an AI-generated image. And I want to start this talk with software, because the world becomes software. We see software in everything today, and we see also that software is getting more and more complex. So all the applications that we know that we use are getting bigger, are getting more complex. And I've just chosen the example of the Multics kernel. 40 years ago, 1983, it had 250,000 lines of code. And if you compare that with the Linux kernel of today, from 2018, it was 25.3 million lines of code. So already there we see increase in size and increase in complexity. What we can also see is a softwareization of hardware. So this means that more and more functionality today is realized in software, where it was done in hardware before. And a huge driver also for this increase in software all around us is this topic of connectivity and the Internet of Things. With all the devices getting connected and available everywhere, this is also driven by software. And this doesn't stop when we talk about medical devices. And the market and customer expectations for medical device software are also rapidly evolving in this environment. You have the request for regulatory compliance and safety, especially with the IEC 62304, the international standard for medical device software. You have the request for interoperability, so all these devices have to work together. They have to be easy to use with user-friendly interfaces. We have data security and privacy requirements. Healthcare is still the sector that is struck the most by cybersecurity and cybercrime, so there is a high demand for that. We have real-time data and analytics, cost effectiveness, and continuous updates and support. And then let us take a look at what is the expectation, how a modern application should look like. And I didn't take a medical device. I took something that we can better associate with maybe architecture. And here we see a modern building. And it is built to provide connectivity. You have lots of antennas. You have efficiency. It is efficient, energy efficient with solar panels on the roof. It has a comfortable interface. It has a modern architecture. It is accessible, and it also provides a certain level of security. But does it really look like that in reality? Let's take a look behind the scenes. And then we see how modern applications also can look like. They are not made from scratch. They are built around a main processing that has grown over many years. You have even some initial foundations around that maybe already start to crumble. Nobody really knows what they have been made for, but they are still there. Nobody wants to touch. We already have some fortifications integrated into that, some modern extensions, and over the years also small additions have been made. So what we have to deal with here is legacy. And first we have to answer the question, what is legacy? Because there are multiple interpretations what legacy can be, especially when we take a look at legacy code. So legacy code is legacy as soon as it is written, or that gets inherited by a team or a program from somewhere else, or code no one wants to deal with anymore, or code without tests. I found one definition that I prefer, and this is this one. It is code written by others or under a previous language, architecture, methodology, or framework that pertains to the current project. So it's something that we take over for the current project. Now, in the context of the IEC 62304, we have to separate the term legacy from the term SOUP, S-O-U-P, software of unknown provenance. So legacy in terms of the IEC 62304 is medical device software that was designed prior to the existence of the current version of the standard and that has insufficient objective evidence for compliance. So we already have some information in the use of this software in the medical market. On the other hand, the software of unknown provenance, the SOUP, it is a software item that was previously developed. If it had been developed for medical, adequate records of the development processes are not available or not developed for the purpose of being incorporated into the medical device. There was one side note concerning SOUP. The whole software system, the whole medical device software cannot be declared as SOUP. The requirements for SOUP, just shortly explained, you have to specify the requirements for the software of unknown provenance, the performance requirements, and then you have to monitor that, put it in a monitored environment, and then watch how it behaves in practice. There are advantages of reusing legacy code. First of all, it's cost efficient. You already have the software, it is working, you don't have to redevelop it, so cost efficient. Proven reliability, it has been around already for quite a while, so you already have a certain degree of confidence that there is not so many bugs in there. Also, risk mitigation. With each new development, there is the risk of building something that contains bugs. As it has already proven reliability, it's a matter of risk mitigation to stay with what you already have. Also, knowledge retention. You already have built the knowledge and you have incorporated the knowledge into the source code. So you have to not reinvent the wheel, just reuse. Also, faster time to market. It's already available, just reuse it. Compatibility, what you already have implemented, you don't have to do again. It sounds like saying always the same. If you already have it, you can reuse it. And then the last point, resource availability. You don't have to put an X number of developers into the project to develop the software from scratch or new. But it somehow feels like a skeleton in the closet. So you have built it, it's been there around for quite a while, but it's always the feeling that there might be something that has not yet appeared, that has not yet come up. So there's always this fear maybe of that there is something in the code that you are not aware of. And so there are some issues and problems connected to legacy. As it is fully built and maybe around for quite some years, quite a while, the people that know why they have done something may be no longer around. So you have high maintenance cost. You always have to investigate, what does this code do if I want to change it? Then you have incomplete and missing documentation. It is not developed according to the current version of the standard, so there is documentation missing. Missing compliance comes with that. Insufficient safety and security, as already mentioned. The medical sector is the one that is struck the most by cybercrime, and cybercrime gets worse over the years. Let's say if a system is unprotected or unchanged on the market for many years, the risk that it is exploited is getting higher. You have very limited integrability and expandability. It may be compatible with what you have had before, but if you want to integrate it into a new environment or expand it with new functionality, we come back to the point, high maintenance cost. You have to investigate how to do that, and it costs a heck of a lot of money. And also a problem that may occur is expiring support, end of maintenance period, or end of the product life. So you have it around for quite a while, and we all know that parts of the hardware that the software is running on may reach their end of life. So you have to touch the software, you have to redevelop it, and then you are faced with the challenge of dealing with the legacy. And legacy, in terms of the IEC 62304, it is specifically addressed. And they call it the balance of benefits. When you deal with legacy for medical device software, if you want to put a new device on the market, develop new software, then you have to balance between the benefit of applying the software development process according to the standard to the risk of introducing new defects by modifying the existing code. And there are ways to deal with that risk. And the standard itself says, for example, detailed design and unit verification reduce risk, primarily during the process of developing new software or refactoring existing software. So unit verification for reduction of risk for refactoring of existing software. And then when we talk about legacy code, there is one famous author, Michael Feathers. He has written a book dealing with legacy software and legacy code. And I will quote him in two places here. And he says, covering software means covering it with tests. When we have a good set of tests around a piece of code, we can make changes and find out very quickly whether the effects were good or bad. So that means without test cases to verify all paths, a one-line fix can break the integration build, leading to a chaotic debugging frenzy. So, when we want to deal with legacy code, we have to find a way to change it, to modify it, and that we know that we have changed the behavior, and we do that with tests. And this comes along with the questions how to create the test cases for the legacy code. And then we know we have to modify it, and this raises the question how to efficiently improve the legacy code. And the first topic that we have to talk about when dealing with the legacy code and then creating test cases is the topic of characterization tests. And again, I will quote Michael Feathers, and he says, most types of testing have the quality of being about correctness. We test our code to see that it is doing what we want it to do. This assumes that we know what it is supposed to do, that we have some sort of specification in our heads or elsewhere that tells us what we are aiming for. But what if we don't? Unfortunately, this is exactly where we are with a lot of software. We need to make changes to it, but we don't know enough about what it does. And this is where he introduces this term of characterization tests. Characterization tests are specifically made to characterize the current behavior of code using tests. And they are made to protect legacy code against unintended changes. So the first thing we have to do is create characterization tests to capture the current behavior of the code, and then we can modify the code and see if the effects were intended or not. And for creating these test cases, we can use ATG baselining to create a baseline. I will explain in the next slide what that is. And then we will have a regression test suite. And we can do this baselining. I mentioned the term ATG. ATG stands for Automatic Test Case Generation. It is a possibility to automatically generate high coverage test cases from the source code. We have that integrated in one of our tools, that is VectorCAST, our unit testing solution, and there it is integrated as a background process. You just have to create the environment and then you can trigger the ATG. And then the second part of this term, ATG baselining, is baselining, and this extends the ATG generated tests to have expected values. And now with that we have the characterization test that we need and that will support us in refactoring or porting legacy code. Because we have captured the current behavior of the code, we know exactly when we put in this value we get this output, and then as soon as we change the behavior in a way that input to output the relation is different, we will have test cases that fail and we will have known that there were changes that we maybe did not foresee. And the aim of this ATG baselining is to have a cleanly passing test script at the end. So it's really drawing a baseline, assuming the current behavior is the one that we want to keep. And how do we do it? You can just execute a command line once you have built the environment. You see it down there. It's as easy as that. And the idea, how do you work with that, is you run it once to get your tests, and then you put them under version control, you lock them down, and then maintain the generated tests manually when the code changes, so that you understand which test cases you have touched and what you have done before. So then we have the regression test suite. But then running always all the test cases may also be not the best way to deal with your software, deal with your legacy code, because this can take a lot of time. You will end up with, let's say, thousands of test cases, and running all of them each and every time you change the code is not efficient. And for that, we can use change-based testing. So change-based testing in general is an approach when you take a look at your test cases and your source code. When you do a small change in your code, it is possible to clearly identify the test cases related to this line of code that has been modified. And then just rerun these test cases. So it helps you to narrow down the number of test cases you have to execute with each execution, with each modification of your source code. So it reduces the test time, it improves efficiency, and improves infrastructure utilization, improves time to market, because instead of running thousands, you maybe just have to run 10 or 12 tests, and with that it improves also the quality. So now we have created the test cases and we know how to execute them. Now we can modify the source code. But how to efficiently improve the legacy code? Because currently we are standing in front of a huge pile or knot of things that we can change. We now have the possibility to do it, but where to start? Which thread to pull? Where do we start with fixing this huge pile of work that we have now in front of us? So when we modify the code, why not do it efficiently by analyzing the code and then identifying the spaces or the lines of code, the code modules that are worth improving the most. Let's put it like that. So we can use for that quality metrics, like for example technical debt, to identify which modules, which components of our legacy code require refactoring. But why am I now talking about technical debt? I will come to this. Let me first explain what technical debt is. So technical debt arises when measures to ensure and enhance technical quality are not carried out. And this includes, among other things, the postponement of documentation, the omission of complete module or regression tests, the disregard of compiler warnings, the insufficient or missing adherence to coding guidelines, too high complexity of the code, and code repetitions. But what has this to do with the IEC 62304, medical device software? Addressing these shortcomings helps fulfilling these requirements. Let me explain. When we address missing code documentation, IEC 62304 is asking for detailed design, so for a clear documentation of your source code. So addressing this missing code documentation will help you addressing this need. Incomplete module and regression tests. Tests based on requirements and detailed design contribute to the unit verification process and serve as acceptance criteria and unit verification. Compiler warnings, when we talk about code and dealing with it, existing compiler warnings, they indicate a risk, and fixing these compiler warnings serves as a gap closure activity. Missing adherence to coding guidelines, compliance with standards serves as unit acceptance criteria. And high complexity of code and code repetitions, improvements enable better testability, and to establish unit verification process and unit verification itself. So all of these issues that are addressed when we talk about technical debt help us to fulfill the IEC 62304. How can we do that? And there is no complicated setup needed. You don't need hundreds of tools or setups or something like that. We can start very small to deal with that. For the missing code documentation, we can use a code analyzer or a static analysis tool to measure comment density. For the incomplete module and regression tests, we can use a testing tool to achieve code coverage. But let me shortly just emphasize this. With characterization tests, this is not the code coverage we need to have in the end. We need requirements-based test cases, just to mention that. So in the end, we have to map our test cases that we want to use here to requirements. Compiler warnings, we have the compiler that issues the warnings, so we will just use that as indicator. For missing adherence to coding guidelines, we use traditionally a static analysis tool to measure the adherence to coding guidelines, and we will use the coding rule violations as indicator for that. The high complexity of code, there are also metrics to measure that. For example, the NPath metric, the V of G, this is the cyclomatic complexity, and they can be measured using code analyzers or static analysis tools. And also for code repetitions to find textual and algorithmic duplicates, clones in the code, we can use a code analyzer. So basically it's just three tools that we need here, something to test, something to analyze code findings, and something to measure some metrics of the source code. So using that information, we can build up an analysis pipeline. At the start, we have the source code, and then we are using the static analysis tools to measure the adherence to, for example, coding guidelines, to measure metrics, and to detect cloning. And then we need to analyze this information to put it together that in the end we can make something out of these results. So we're using in a second step the results analysis, for example, using a data intelligence tool, and analysis methods and models like SQUARE, which is the ISO 25000 series, and SCALE, software quality expectations based on lifecycle expectations. So that gives us an indicator which quality characteristic has to be fulfilled when in the development lifecycle. And this pipeline gives us then in the end the technical debt as a measure that we can use to identify code that needs refactoring. Some short words about data intelligence, what is behind that. So data intelligence is a family of solutions and tools that analyze and consolidate the available data, and that will help you to gain valuable insights and to derive target-oriented actions and priorities. Once we have measured the technical debt, these data intelligence tools can visualize the results in a way that it is easier for us to identify the hotspots where we need to go next, where we need to work first on. For example, on the left side, you see the scale pyramid, and on the right side, you see a visualization by density per function, just a different way how to show the density and the technical debt related to, for example, your functions. And then based on this scale method, we can show it in this pyramid, but we can also map the technical debt we have assigned to these characteristics. We see the characteristics on the side of the scale pyramid, starts with testability, and we can measure that per function. And this helps us to identify where do we have to look first. Because these data intelligence tools can provide us with detailed listings and sortings of all relevant artifacts based on these characteristics that we have to deal with. So it can help us to answer the question where to look first. And then when we know where to look first, we can also take a detailed look at this where and see what do we have to do first. So we can break down the findings that we have to algorithmical artifacts or test cases or requirements. So whatever we put in as data into the data intelligence tools, we can map the findings and the depth to this. And then once we have this overview and know what to do, then we can modify the code, and then we can use the regression test script that we have generated before using the baselining and the existing test cases to monitor the test results while we modify the code. And there are also metrics and measures in the data intelligence solution that can help us in doing so. For example, the test gap analysis. This will help us to identify the relation between code and test results. And it will show us, for example, if the code has changed but the test results are not compliant, this will be highlighted in this test gap analysis. So this helps us to identify areas where we had unintended changes, for example. And these data intelligence solutions can even take it a step further. They can visualize the evolution and trend over time. So here we see, for example, the technical debt overall trend, and we see it reducing over time. And we can also plan, monitor, and adjust that, and even automate it. So here we see the planning of a technical debt objective. And we see that we have not yet reached our goal, so we are out of the target range. And if we integrate this as a quality gate into our build pipeline, you see an example on the upper right corner of the slide, then as soon as we are out of this target range in an important point in time, then we can stop the development pipeline, stop the building pipeline and say, okay, we have not reached our target objective. So we have done something wrong. We are not where we want to be. So bringing all of this together, how to deal with the legacy code when we have the source code that we want to modify. And now we know how we could do that. On the one side, we can create the test cases using the ATG baselining. And then we know that when we execute the test cases and we have done modifications to the code, we know exactly the effect that it had on the source code. So change-based testing to efficiently execute the test cases. And on the second loop, we have the information how to efficiently improve the legacy code. And we'll use the quality metrics to identify code that needs refactoring and the data intelligence to make sure that we are making it better. And with all of that, don't just reuse, make it better for the next time. So with that, thank you very much for staying with me until the end of this presentation. And if I have piqued your interest, you can find links down in the description that will take you to our website, vector.com or vectorsoftwarequality.com, where you find more information about our solutions and products. For example, PCLint Plus for static analysis, VectorCAST for unit testing, or SCORE for data intelligence. They can also get in contact with us or subscribe to our newsletter to be informed about our upcoming events and new releases. And until then, enjoy coding.